Ooh, this slide is fancy. I would add music here, but I'm not really sure how, so, let's just get on with it. So this video will be based on the video that we did previously on deriving the Fourier series. So we'll use a lot of concepts from there. And so what we're going to do in this video is derive the Fourier transform using this Fourier series that we derived. Let us begin with a summary of what we discovered after deriving the Fourier series. In order to derive the Fourier transform, it is best that we use the complex exponential form of the Fourier series, as displayed in this red box. So as a refresher, what we did in the previous video with the complex exponential Fourier series is that we defined an inner product over which an infinite set of complex exponential basis functions is orthogonal. And then we use this orthogonal set to express a periodic function, f of t, with period t as a linear combination of these orthogonal basis functions. So again, it's really important to note that outside of the bound of t values, from t0 to t0 plus t, the Fourier series, based on how we derived it, because of the periodic nature of the basis functions and the resulting periodic nature of the Fourier series due to the linear combination of the basis functions, because it preserves the period of all those basis functions, the Fourier series will automatically fill in the values of the rest of t based on the assumption that f of t is periodic with period capital T. However, this isn't always the case. It's not always periodic with period t. So in the Fourier transform, we're going to try to kind of modify our Fourier series formula so that fits the more general case of a function not being periodic with period t specifically. And you'll see how we do this. It's pretty clever. So recall that what we're doing is sampling functions to create vectors. So we're only actually taking a sample from x is equal to a to x is equal to b. So we're only taking a finite sample over the domain of the function. But in this video, we're actually going to sample over the entire function, and you'll see that later. And also remember that the bounds of the inner product from a to b specify the range of x values that we sample to obtain our vectors. So the inner product is what specifies this range of x values. And so in the Fourier series, we sampled t values from t0 to t0 plus t to form our vectors. So what does this mean? It means that the Fourier series can only accurately represent any arbitrary function within the interval of t0 to t0 plus t. And of course, for periodic functions with period t, the Fourier series will actually accurately represent the entire function for all values of t. And the reason for this is because the Fourier series representation will automatically fill in the correct values for the function outside of the bounds of t0 to t0 plus capital T, if it is a periodic function with period t. Since the series representation will also be periodic with period t due to the periodic nature of the basis functions and the fact that the linear combination of these basis functions, in the linear combination of these basis functions, the period is preserved, or the periodic nature is preserved. So aka both the series representation of the function and the function itself assume the same values outside of the t interval from which the function is sampled based on the rule for periodic functions that I was talking about earlier with period t, that f of t is equal to f of t plus capital T. So how can we generalize the Fourier series? In other words, how can we represent any arbitrary function accurately for all t values in its domain using the Fourier series that we derived in the last video? So how can we represent any function, even if it's not periodic, with period t? And this is actually simple. We set t0 and capital T such that we create a vector containing all values of the function from negative infinity to positive infinity. This means that there are no unspecified t values for the Fourier series representation of the function to fill in automatically. So this means that all t values are known. There are no gaps in our information, so we don't have to fill in anything more. Yeah. So if we were to do this, then we would be extracting our vectors over the domain of the entire function instead of a small snippet of the function. Specifically, we need to set values for t0 and t such that t0 is equal to negative infinity and t0 plus capital T is equal to infinity. This will change the bounds of our inner product and thus will change our Fourier series. As shown in this slide, this substitution of substituting negative infinity and infinity for our lower and upper bounds respectively will change our inner product so that it no longer has bounds. So what we've done is that we've generalized the Fourier series to non-periodic functions, because functions that aren't periodic have a period of infinity. So we've actually generalized by setting our bounds to specific values, which may sound a bit counterintuitive, but that's what we did, and it makes sense. So for our Fourier series representation of our function, we originally had this, but now we have this, and it's a result of setting our bounds to negative infinity as the lower bound and positive infinity as the upper bound. So we're taking, so we're sampling from the over all values of t over the entire domain. So we're creating a vector that represents the entire function this time. And we're taking the limit as t approaches infinity over here because we had to set t equal to infinity in order to set the upper bound equal to infinity. And t is the period, so we have an infinite period. So now we will set this, we'll take this and we'll put it over here. So here we have our generalized Fourier series, and we can process it down further. We could recognize that 2 pi over capital T, where capital T is the period, is equal to omega naught, where omega naught is the fundamental angular frequency. And we could substitute omega naught into the equations, and we could recognize that the limit as capital T approaches infinity is equivalent to the limit as omega naught approaches 0. So let's move what we have up to here. So let's process this further. In the green box, we will define a variable called delta omega, and this will be the difference between omega naught multiplied by n for the next value of n and the current value of n. And we will see that delta omega is equal to omega naught. We will also define omega, which is the limit as delta omega approaches 0 of delta omega multiplied by n. And something interesting here is that omega, if we define it this way, is actually a continuous variable, even though n is an integer, because as delta omega approaches 0, you'll be going up by very small steps, and this will approach a continuum. So if we make the substitution of delta omega for omega naught, and we keep in mind the definition of omega, then we have this over here. And let's move it over here. More processing. So we will define capital F of delta omega times n to be c sub n over delta omega. And so now we have this over here as displayed in that white box. Also keeping in mind that omega is the limit as delta omega approaches 0 of delta omega multiplied by n. And let's move this up over here. And here we will perform the final steps in obtaining the Fourier transform. So we're going to substitute in omega, and if we recognize this finite summation over n as an integral, and we also make that substitution, then we obtain the Fourier transform. And that's basically it. We obtained the Fourier transform, which is pretty cool. And here we have generalized the Fourier series to not just applying to periodic functions with period capital T, but for any function, or at least most functions, I think. I'm no expert, so I don't really know for sure. But yeah, so we did this by leaving no ambiguity for the T values. So what we did was that we sampled over the entire domain of our function. So no T values were left unspecified. And this is important because if we left any kind of T value unspecified, then the Fourier transform will automatically fill in those values according to the rule for periodic functions with period T. And that period is the same as our basis functions that we use to create the Fourier series and our inner product. And this will be that f of t is equal to f of t plus capital T. So it will fill in these values according to that rule if it falls outside the range of t naught as our lower bound to t naught plus capital T as our upper bound. Or in other words, our sample that we took throughout, for just one period. So yeah, so we left no ambiguity in the T values, and we could have just set period T to infinity. However, if we just left T naught unspecified, then all values before T naught would be unspecified, meaning that the function would just automatically fill in those T values, so it wouldn't necessarily represent the entire function. So by doing the Fourier transform, we now represent the function over the entire domain, which is pretty cool. And yes, that's it. And remember to have a great day.